Hey, Michaela. So the problems that we did in lesson 92, they're building on what you've previously learned, right? So if all of the example is not given, it's because it's already been given in a previous lesson. And I promise you that all the information that you need is in the problem. You just have to think it through. Don't forget to use your table and to draw your picture. So let's go through these. So the first one you said you had a problem with was this one, the Voltaire problem. On Monday, Voltaire drove to town at 60 miles per hour. On Tuesday, he drove to town at 40 miles per hour. So to town and then to town. So that tells me he went the same distance. So this is going to be a distance problem with equal distances. So the distance on Monday is equal to the distance on Tuesday. And we know we can break a distance equation down into rate times time. So the rate of Monday times the time of Monday is going to be equal to the rate on Tuesday times the time on Tuesday. This is where we want to get into our picture and our table. So our picture is going to look something like this. On Monday, he went to town and he went 60 miles per hour. Tuesday, he went to town, same place, same distance, but he went 40 miles per hour. That's all that we have so far. Now, the last sentence says, if the total traveling time for both trips was 15 hours, how far was it to town? So we know that the time for Monday plus the time for Tuesday was 15 hours. That's the total traveling time for both. Got to look for those keywords and really think about what the sentence is telling you what to do, okay? All right, so now let's create our table. We have the rate and we have the time for Monday and for Tuesday, right? So here's our little table. And you don't have to draw all these lines. I'm just doing it because I want to. So we know that the rate on Monday, the rate is another word for speed. So the rate is 60 on Monday. And on Tuesday, his rate or his speed is 40. Now, I don't have individual values for time, but I can create a substitution value by subtracting one of these from the total. So I'm going to subtract the total time on Tuesday from both sides. And what that does for me is it finds the value of Monday's time. So the time Monday is equal to the total 15 hours minus whatever the time was on Tuesday. So these are going to be my values. So the time on Monday is 15 minus the time on Tuesday. And the time on Tuesday, we don't know what that is, so it just remains the time on Tuesday. These are my substitution values for my equation. So you have all the information you need to solve it. So what we're going to do is I'm going to put in for the rate on Monday, 60. The time on Monday is 15 minus the time on Tuesday. The rate on Tuesday was 40. And we still don't know what the time on Tuesday was. Now I can solve it, though, for the time on Tuesday. 60 times 15. I don't know what that is. It's a really big number. 60 times 15 is 900. Minus 60 times the time on Tuesday, because this is a negative, this is a negative. And that equals 40 times the time on Tuesday. I'm going to add 60 to both sides. This cancels. That leaves me 900 is equal to 100 times the time on Tuesday. If I divide both sides by 100, 9 is the time on Tuesday. So now I know what that is. So this is going to equal 9. In fact, I'm just going to erase this and put 9 in here. Now, I could substitute in and say 15 minus 9 equals 6. I could, but that's not what it's asking me for. It's asking me for how far was it to town. So I need to find the distance. And since I have both numbers for Tuesday, I know rate times time equals distance. So 40 times 9 is 360. That's my distance. And the other thing, since it's a good idea to check your work, we know that they're supposed to be equal distances. So if TM is equal to 6, we can check it. 60 times 6 is also 360. So the distances are equal, and we did the math correctly. This is going to be your answer. How far was it to town? 360 miles. You just have to type in the number. Next problem. All right, in this next problem, we have two people crawling to the barn. They crawled to the barn and then hopped back. So they went to the barn and back. Excuse me. They crawled at 300 centimeters per minute and hopped at 400 centimeters per minute. And it gives us a total time. So we're going to do the same thing we did last time. We don't care that it's two different people. We care about the way they went, because the distance on the way there, the distance crawling, that's to the barn, is equal to the distance hopping on the way back from the barn. So our picture looks like this. Crawling, here's the barn. They left the barn, came back, hopping. The distances are the same. The difference is going to be the speed in which they do both of them is going to affect the time. Okay, so they crawl. Let's go ahead and start our table. Rate, time, crawling, hopping. So I'm just going to draw my middle lines in here. So my rate crawling, it says they crawled at 300 and they hopped at 400. So their speed is 300 for crawling and 400 for hopping. If the round trip there and back, the time there and the time back was 7 minutes, okay, so the time crawling plus the time hopping is equal to 7. How long did they crawl, and how far was it to the barn? So this is this. That's all we have. And we have their rate. That's all we have to work from. And we have a total amount of time. We're going to do the same thing we did before and create a substitution value by breaking the total up by subtracting one of the components. We take that away from both sides. The time crawling is equal to the total 7 minutes minus the time hopping. So this is our value for the time crawling, 7 minus the time hopping, and our value for hopping is just the time hopping. We don't know how much that was. We can break these equal distances into two parts, rate times time. So rate crawling times time crawling is equal to the rate hopping times the time hopping. The rate crawling was 300. The time crawling is 7 minus the time hopping. The rate hopping is 400, and we still don't know the time hopping. Now we multiply. 300 times 7 is 2100 minus 300 TH is equal to 400 TH. I add 300 to both sides, 300 TH that is, and I get 2100, because these cancel, is equal to 700 TH. When I divide both sides by 700, I should get 3 is the value of TH. So if 3 is the value of TH, then I can substitute that in right here. I put 3. 400 times 3 is equal to 1200. So that is the distance, because rate times time is equal to distance, right? So that tells me it is how far it was to the barn. Is distance is equal to 1200. And if the round trip took 7 minutes, then how long did they crawl? Well, 7 minus TH. TH is 3. So 7 minus 3 is 4. So it took 4 minutes crawling. So crawling equals 4. So those are going to be your answers. So everything you need is in the problem. You just have to tweak it a little bit. You have to create your own substitution value from the information that's given. And if you start by drawing your picture, it helps you write your equation. Then you break down your equation and take your stuff from your table, your information from the table, including your substitution value, and drop it in. That's how we're doing these problems. Let's do one more. So here we have another problem. We have Joyce. And Joyce drove to the lake at 30 miles per hour. So we can start making our table with that. All right, so our rate and our time. We're not sure exactly what we're recording here. So we're going to just start with the first bit of information. She drove to the lake at 30 miles per hour, but she made the long walk back at 4. So it's the same person doing both things. So she drove to the lake, and then she walked back. Okay, so this is Joyce, and she drove to the lake. Here's the lake, and then she walked back from the lake. So the distances are the same. So that means I've got the distance that she drove is going to be equal to the distance that she walked. So it says that she drove at 30 miles per hour, but she walked at 4 miles per hour. So how long did she walk if she was gone for 17 hours? So the total of these two times is 17 hours. That tells me the time driving plus the time walking is equal to 17 hours. So I'm going to create a substitution value by subtracting the time walking from both sides. So the time driving is equal to 17 minus the time walking. So 17 minus the time walking, and we still don't know how long the time walking was. But now we have the 4 pieces of information we need to substitute into this equation. We have rate driving times time driving is equal to the rate walking times the time walking. So we can put in for RD is 30, TD is 17 minus TW, RW is 4, and we still don't know what TW is. So again, we do the distribution. 30 times 17. Sorry, that's my dog. He likes to bark when people ring the doorbell and deliver things. He's so loud. All right, I'm going to add 30 TWs to both sides. I get 510 is equal to 34 TWs. So if I divide that by 34 on both sides, I find that TW is equal to 15. Okay. So if, let me use this right down here. how far did she walk? Well, in order to find out how far she walked, we have to put in our time. So 4 miles an hour times 15 hours, that's going to be 60 miles. So that's one answer. And how long did she walk? She walked for 15 hours. That's the other answer. So she walked for 15 hours and she walked 60 miles at 4 miles an hour. It's pretty fast walking. That's pretty fast walking in my opinion. Okay, that's how you do these. You keep doing the same thing over and over again. Make your picture of what happened. Create your table. If it's equal distance, then they're just distance of this one is equal to the distance of this one, and then you break it down into rate times time for this distance and rate times time for the other distance. Then you can reread the problem to find the information for your table. But you got to kind of read it through twice to find the picture and figure out what you want to label the two trips. Whether it's a person or whether it's the mode of traveling, either one of those. What matters is finding out your distance there. All right, let's look at another one. All right, so here we have Alphasia, and she was headed for the rodeo at 9 a.m. All right, so this one's a bit different. It has two people. So let's read the problem. Alphasia headed for the rodeo at 9 a.m. at 30 miles per hour. So that gives us a good picture of Alphasia. So let's start with Alphasia. We know there's going to be somebody else in the problem because that's the way the problems work. And she, excuse me, I'm still getting over the flu. I can't get rid of this stupid cough. It just keeps hanging on and it's frustrating. She's headed to the rodeo and she's going at 30 miles per hour. Okay, that's where she's headed. What time was it when Bubba caught Alphasia? Hang on, there is some information missing. What happened? Oh, I see what it is. It didn't copy all of my stuff here. Something wrong with my thing. All right. Let me get that the right size. That should be 35. And this is just duplicating that last question. Okay, so now we can see all of the question because I knew it was in there. Okay, so now let me get my pen back. She left at 9 a.m. At 11 a.m., Bubba headed after her. So Bubba left at 11 a.m. and he headed to the rodeo. And he was going at 60 miles per hour. We need to know what time it was when Bubba caught her. So we know their distance is the same because it says they left for the rodeo at the same time or at the same place. It's assumed it's the same place. Whenever it doesn't tell you, it means they left the same place. Assume they live in the same house. Okay, so the distance of Alphasia is going to be equal to the distance of Bubba. Especially since we know that all of these are equal distant problems. So now we're going to do our table. Rate, time, Alphasia, Bubba. We know her rate is 30. We know his rate is 60. It does not tell us the total time. We don't have any idea. But we do know that the time of Bubba is 2 hours less than Alphasia Or we could say that the time of aphasia is 2 hours more than Bubba. So I think I'm going to do that. The time of aphasia, hang on, I wrote that wrong. The time of aphasia is Bubba's time plus 2 hours because she left 2 hours before he did. She left at 9 and he left at 11. He left 2 hours later. So the time of Bubba is just the time of Bubba. You could also write this differently, right? The other way to write the time would be the time of aphasia is the time of aphasia, and Bubba's time is the time of aphasia minus 2, because he left 2 hours after she did. This is how you would write it to say he left 2 hours after she did. This is how you would write it to say she left 2 hours before he did. It's just depending on whose time you're calculating it from. It does not matter to the problem. Whichever way you do it, make sure it makes sense. If you're using Bubba's time, then you have to add for her. If you're using aphasia's time, you have to take away for him. Okay? So it doesn't matter which one you do. What matters is that you apply the two correctly, the difference in time to the right one. And you have to think about it for a minute, right? You have to really look at it. Okay, so this is our table. This is what we're going to solve with. So I'm going to put the rate of aphasia times the time of aphasia is equal to the rate of Bubba times the time of Bubba. The rate of aphasia is 30, and the time of aphasia is Bubba's time plus 2. Then we have the rate of Bubba, which is 60, but we don't know the time of Bubba. But we can solve now. So we have 30 times the time of Bubba plus 60 is equal to 60 times the time of Bubba. I'm going to subtract 30 from both sides. I have 60 is equal to 30 times the time of Bubba. Okay, so divide both sides by 30. 2 is the time of Bubba. So 2 hours. 2 hours is how long he traveled. So if he traveled 2 hours and he started at 11 a.m., 11 a.m. plus 2 hours is going to be equal to 1 p.m. because then you would go to 12 p.m. and 1 hour later would take you to 1 p.m. Right? Plus 1 hour plus 1 hour. So 11 a.m. plus 2 hours is 1 p.m. This is your answer. 1 p.m. You have all the information you need to solve it. Let's look at the last one. Okay, last one. Billy ran to town at 8 kilometers per hour and then walked back home at 3 kilometers per hour. So our picture is this. Billy, he ran to town. Here's town. And he went there at 8 kilometers per hour. So 8 kph. And then he walked back home. This is home. And he did that at 3 kilometers per hour. How far was it to town if the round trip took 11 hours? So the time running plus the time walking is equal to 11 hours. So we can create our substitution by subtracting the time walking from both sides. The time running is equal to that total 11 hours minus whatever time he was walking. So now we see the distances are the same. So the distance running is equal to the distance walking. The rate running times the time running is equal to the rate walking times the time walking. So the rate, let's do our table. Rate, time, running, walking. The rate running was 8. The rate walking is 3. The time running is 11 minus TW. And the time walking is just TW because we don't know what that is. So 8 times 11 minus TW is equal to 3 times TW. And if you look, you can see 8 times this is equal to 3 times this, right? It almost looks set up for you. We just have to put it on either side of the equation. So now we multiply. That's 88 minus 8TW is equal to 3TW. If I add 8 TWs to both sides, I get 88 is equal to 11 TW, and if I divide both sides by 11, 8 is equal to TW. So, how far was it to the town if the trip took 11 hours? His time walking is 8. 3 times 8 is 24. So 24 kilometers is the answer. We're looking for 24. And because we know that this distance is equal to this distance, we don't have to solve this one because they're the same number. But we can prove it to ourselves. We could say 8 times 11 minus 8. Well, that's 8 times 3. That equals 24. It matches. We did it right. Okay? All right, that is the last one. If you have any questions, please ask. Keep asking. You're doing a great job asking. And I hope to see you tomorrow.